All right, good morning, everyone. Today's December 17th. We're going to do Unit 6, Lesson 1. So we're talking about average rates of change. So let's do some terminology. What is rate of change? Rate of change is a measure of a change in one quantity, the dependent variable, with respect to a change in another quantity, the independent variable. So example of rate of change could be something like if you have a distance time graph and you're calculating speed, because speed is the difference in distance divided by the difference in time, right? So secant is a line that passes through 2 points on a graph. So you pick 2 points on any function or a graph, and then you just draw a line between them. That's called a secant line. A tangent line is a line that touches the graph of a relation at only 1 point within a small interval. So a tangent line, you pick 1 point on this graph or function, and then you draw a line that only touches the graph at exactly that 1 point. That's called being tangent. An average rate of change is a change that takes place over an interval, while an instantaneous rate of change is a change that takes place in an instant. We will focus on average rates of change in this section. And an average rate of change corresponds to the slope of a secant between 2 points on a curve. So we're basically going to find the slope of secant lines. Here we have the formula. It's just basic formula like rise over run that you should have learned in grade 9. So average rate of change is equal to the slope of secant, which is just the difference in y over difference in x, which is y2 minus y1 over x2 minus x1, which is also rise over run. So once you have your 2 points, pretty straightforward, nothing too difficult. So let's go to part 2 here. All linear relationships have a constant rate of change. Remember, first differences for linear rate of change, same. Average rate of change calculations are over different intervals of the independent variable give the same result. So this is for a linear relationship. We will be focusing on nonlinear relationships. Nonlinear relationships do not have a constant rate of change. Average rate of change calculations over different intervals of the independent interval give different results. So they're basically saying that if you have a nonlinear function, depending on your 2 points that you choose, you can have very different slopes. So let's do example 1 here. Example 1. Andrew drains water from a hot tub. The tub holds 1,600 liters of water. It takes 2 hours for the water to drain completely. The volume V in liters of water remaining in the tub at various times t in minutes is shown in the table and graph. Alright, so we have a graph here, and we have a table with all these points. This is clearly not linear, and we're going to ask for the average rate of change between 30 and 90. So how do we figure this out? Easy. Remember, slope is just your y value, y2 minus y1 over x2 minus x1. And in this case, your y value is volume. So this is just going to be volume v2 minus v1 over t2 minus t1. And what are my values for v2 and v1? Well, 30 and 90 are my two intervals. So 90 is v2. And 30 is v1. So my t value is going to be 90 minus 30. But my actual volume at those points is going to be 900 for 30 and 100 for v2. So it's 100 minus 900 over 90 minus 30. Which is basically negative 800 over 60. And we expect a slope because you can see that it's going down, right? Like it's a negative slope. So that's good. We're expecting negative slope. When we're going to write in terms of values and words, we don't really necessarily write the rate of change as a negative rate of change. I mean, we do. Sorry. Let me fix that. It is negative 13.3 liters per minute. But when we're writing like our thesis statement, we should write the volume of water is decreasing by 13.3 liters per minute. If you understand that. So here, I'll write it out so you can see. So the volume of water is decreasing by 13.3 liters per minute. So instead of writing negative 13.3 liters per minute, we are saying it's decreasing because that's essentially what's happening. So yeah. And now we're going to do the exact same thing, except for a different set of intervals. Now we're going to do 60 to 90. Same thing. We know slope is V2 minus V1 or T2 minus T1. T2 in this case is still 90, T1 is 60 now. And volume at 90 was still 100 because that didn't change. And volume at 60 is 400. So this is going to be 100 minus 400, which is negative 300 over 30, which is negative 10 liters per minute. And in this case, the sentence is going to be the volume of water is decreasing by 10 liters per minute. So pretty straightforward. The secant, getting the slope of a secant line, it's not difficult. It's really not. It's just knowing the intervals that you're supposed to do it at, and figuring that out from the question. So once again, this is another interval between 90 and 110. I think they're just missing the T. I'm pretty sure it's supposed to be like this. Like that. So typo here. So then yeah, we do it the exact same way. So once again, T2 minus T1. T2 being 110 in this case, and T1 being 90. We know it's 100 for 90, and for 110 it is 10. So that's 10 minus 90 over 20. That gives us negative 4.5 liters per minute. Alright, so the volume of water is decreasing by 4.5 liters per minute. And finally, last example, we have between 110 and 120. Once again, this is a typo. It is supposed to be 110, T 120. So T is between 110 and 120. And we know it's T2 minus T1. And 110 was 10. So I know 10 is going to be here. And 120 is 0. Okay, so that's negative 10 over, I guess, 10. So it's negative 1 liters per minute. Always important to put the units whenever you're doing these type of questions. And here we have our statements. The volume of water is decreasing by 1 liter per minute over this interval. So question now. Does the tub drain at a constant rate? And clearly the answer is no, it doesn't. So the tub does not drain at a constant rate. This can be seen from the graph, which shows a nonlinear relationship. The rate slows as the water empties because of the pressure decrease. This is just us using our common sense to figure out why we think the rate is slowing down. You can see it's very steep here, so the slope is very steep, and it gets a little less steep and a little less steep, and then at this point the rate is almost 0. And obviously the rate does become 0 once the tub is empty. Once there's no more water, can't drain anything, so it becomes 0. So yeah, what else? Something that we all should know, but I'll read it anyways. A negative rate of change indicates the quantity of the dependent variable is decreasing over the interval. The secant line has a negative slope, and then a positive rate of change is the quantity is increasing over the interval, and the secant line has a positive slope. Pretty straightforward stuff there. Let us now do an example in which we are given a word problem. So we have average rate of change from an equation. So a rock is tossed upward from a cliff that is 120 meters above the water. The height of the rock above the water is modeled by this equation, where h is height in meters and t is time in seconds. Calculate the average rate of change in height during each time intervals. So the first interval has been 0 and 1. All we have to do is substitute these values to get our height at 0 and 1. So h of 0 is equal to -5, 0 squared plus 10 times 0 plus 120. And anything times 0 is just 0. So the height, or the initial height at 0 seconds, is 120 meters. Now we're going to figure out h of 1, which is -5 plus 10 plus 120. If I substitute 1 for t, it's just times 1. So this is it. And that's going to be 125. So the height at 1 second is 125 meters. So it went up a little bit, right? Because we're tossing the rock, up over a cliff. So it's in its initial upwards phase. So how do we find the slope? Slope is obviously equal to y2 minus y1, or in this case, h2 minus h1. And h2 is 125. And the initial value was 120. And we know that t2 minus t1 is just 1 minus 0, which is just 1. So the answer is 5. Units are meters per second, because the unit of height is meters and unit of time is seconds, so meters per second. So the initial rate of change is 5 meters per second from interval 0 to 1. Now we're going to do the exact same thing, except the interval is from 1 to 2. So same thing, we're going to substitute h of 2 in here, which I believe is -5t squared, right? Yeah, -5 2 squared plus 10 times 2 plus 120, I believe it was. So 2 times 2 is 4, so this is -20. This is plus 20, this is plus 1, oops, 120. -20 plus 20 cancels out, so the answer is just 120. So h of 2 is 120. So slope is equal to, remember, t2 minus t1, and slope 2 minus, sorry, not slope, height at 2 seconds minus height at 1 second, which was 125. So here we have -5 over 1, or -5 meters per second. Okay, now what? So you'll notice that this is just a lot of practice, a lot of work, time-consuming work. It's not very difficult work, per se. More just, it takes time. So here, -5t squared. So we're going to do h of 3, so -5, 3 squared, plus, what was it, 10 times 3 plus 120, which is 3 squared is 9, so that's going to be -45, plus 30 plus 120, that's -15, and so that's 105. So our slope is going to equal, remember, t2, 3 minus 2, 105 is here, and at 2 it was 120. We've already calculated that, so that's going to be -15 over 1, or -15 meters per second. There we have it. So yeah, basic formula, slope formula, nothing too difficult. All right, good luck everyone.